Welcome to day 5. We're going to study something new called logistic functions. Logistic functions are functions that incorporate exponential growth and decay, but along the same idea with these log functions. It's more a real-life application because some things the population cannot grow forever on forever to infinity, just like if we put fish in a pond or bacteria in a petri dish or whatever. So the main one we're going to deal with in this unit is called logistic growth. And this is the way I usually write it. You're going to have 3 constraints, 3 parameters, A, B, and C. C is the carrying capacity, which you probably have heard in biology before. It's the maximum population that can be affected, or the maximum growth we can gain. B, A, this A times B, this right here, A times B to the T or A times B to the X, this is not the same as an exponential function because it's in the denominator. Another way to look at it, and when we do this on the calculator, we'll do that more probably next class when we do some modeling. The calculator likes to use this form and they give you the numbers for everything, but I'm probably going to stay away from that form because A times B to the T in this denominator is exactly the same as A times E raised to the negative KT over here. So this logistic growth function looks like this little S type of curve. It starts to grow, looks very much like a exponential growth function, and it does keep on growing, but it hits some point where the growth starts to slow down, and at some point you're going to start to level off again. It's very different than an exponential function that grows forever. It is still growing, but as you can see, it's starting to level off. Okay, some key features to this graph. Well, the domain for this graph, it's forever, negative infinity to infinity. The range is 0 to whatever that maximum value is, C. There are 2 asymptotes, 2 horizontal asymptotes. One is y equals 0, and the other one is y equal C. We do have concave up and concave down. Well, we need to talk about that. Well, the concavity is affected by this inflection point. And the y value of the inflection point is half the max. So I do have concave up and concave down. I have up from negative infinity to some x value, and then it's concave down from that x value to infinity. We need to figure out this x. So this x value is f of x is equal to half the max. That we'll have to figure out later. There is no symmetry. And as x goes to infinity, this graph levels off to C. And as x goes to negative infinity, this graph levels off to 0. Okay, and we will work on these functions probably for the next couple days because, like I said, this is a way to me I would model population. There is also a logistic decay function, and the difference is that it's going to start off high at the maximum value of C and it's going to decrease down to 0 in the same S shape as before, but in reverse. We're probably not going to use too many examples that do this, but yeah, you should know what it looks like. So let's look at a graph of one of these. Well, maybe the first thing I should realize is what is the max? I should know what the A, B, and C's are. Well, the A is 4, the B is 0.8, and the C is 10. This B of 0.8 does not mean it's going to decay. It's actually going to grow because it's in the denominator. So since C is equal to 10, that is the maximum value right here, 10. I'm going to have a nice horizontal asymptote of y equals 10. I'm going to also have another horizontal asymptote of y equals 0. Maybe the next thing I should look at is the y-intercept. Well, I just plug in 0 in here. If I plug in 0 in here, I get 10 over 1 plus 4 times 0.8 to the 0. And anything to the 0 is just 1, so I get 10 over 1 plus 4, which is just 10 over 5. So I get the y-intercept is 2. So maybe right around here is 2. After I know the max, I probably should make note of what is half the max. And half the max is 5. That'll come in later because I do need to know where the inflection point is. So after I have all this, I'm going to have a graphical something like this. Right here's my inflection point, so after this I should go concave down and level off. So here's my inflection point. And I should try to find the x of this inflection point. Well, there's a couple ways to do it. One way to do it is on the calculator. Okay, I plugged this into the calculator, and you can see my equation. If you don't know how to use the special fraction key, ask me, and I'll show you how. If you have a really old calculator, it might not have this special fraction key. Now I'm going to graph this, and so I'm going to hit zoom 6. It kind of looks like that. I kind of want to see a better window. So I'm going to change my my x max to 30. I don't need to see a lot of negatives, so maybe it's just -2 for the y-min. And even then, it's not even a great S shape. Maybe I'm going to change -30. Oh, I didn't even change it to 30. Change the wrong thing. Okay, so I want -30 to 30 on the x-min and max, and you can see I get this S-shape look. Now I want to find the inflection point. Well, I know the y value of the inflection point is equal to half the max. Well, that max was 10, so half is 5. I get a graph. I can find its intersection. So right here is the inflection point. As you can see, it's concave up, inflection point, concave down. Second trace, number 5, enter, enter, enter. And I get an inflection point when y equals 5 of about 6.2. So I'm going to go back to my sheet and say x equals 6.2. But I'm actually going to figure this out using algebra in a second. So I want to find the x value of the inflection point using algebra. And so I make y equal to 5. And I'm going to solve this by 5 equals to my logistic function. And then I know this little trick that this 5 on this side can switch spots with this denominator, and this denominator can go to the other side. So I really get 1 plus 4.8 to the x is equal to 10 over 5, which is just equal to 2. I can subtract 1. 4.8 to the x is equal to 1. Divided by 4. I get 0.8 raised to the x is equal to 1/4 or 0.25. And how do I solve when I have the variable and the exponent? I got to do log of both sides. I put log here and log here. This x goes in front. X times the log of 0.8 is equal to the log of 0.25. I can divide by that. I get x equals log of 0.25 over the log of 0.8. I could put this in the calculator. I can put this into the calculator. Clear this out. Log of 0.8. Oops, wrong way. Log of 0.25 divided by log of 0.8. And I get the same x value that I had before. This was the x value I had before. I can even show you when I just hit x. That's the same x value I had before. So I do get it equal to about 6.2. So I've started this next example, and this is an example that uses, instead of a times b to the x, it's a times e raised to the negative kx, or so on and so forth. And I've already started some of the process that the number on top is the carrying capacity, the maximum value. So this is 100. Half of that is 50. I've marked it. I found my y-intercept by plugging in 0. I'm always going to get this S-looking graph. So it goes like this, and then from this point it's going to go concave down. And I need to find this inflection point. I don't know what this x value is. So if I use my calculator, I go 50 equals 100 over 1 plus 3e to the negative 0.5x. Like I said, I can flip-flop these two, get 1 plus 3e to the negative 0.5x is equal to 100 over 50, which is just 2. I can subtract the 1. 3 equals negative 0.5x is equal to 1. I can divide by 3. So I get e to negative 0.5x is equal to 1/3. And because it's an e function, I'm going to natural log both sides. Negative 0.5x is equal to the ln of 1/3. And I divide out, I get x is equal to the ln of 1/3 over negative 0.5. Oh, not x. I'm going to put this in the calculator and see what I get. Here's my calculator. ln of 1 divided by 3 divided by negative 0.5. I get about 2.2. So I get x is about 2.2. Now, if you've been paying attention, maybe you're going to see some trends here. And the trend is that let me grab a different color. This x value was equal to the natural log of 1 over the a value divided by that kind of like negative k value, the number in front of the x. And if we go back to this previous one, a very similar thing, that this x value was equal to the log of 1 over the a value, but divided by the log of the b value. That's what I got here. Okay, let's do some word problems. Putting this all together. So you'll have some more time to do, we'll do some examples with logistics in a second. Let's talk about just general exponentials. Well, from this example, I want to write an exponential formula. I'm going to do y equals a times b to the x. I have to read my information. The original year, x equals 0, is 1940. So when I see this information, 1945, 26, that's 5, 20. And when I see this, that is the year 62, 20,000. So the only way to do this when I don't have the initial value is to make a system. 20,000 equals a times b to the 62 power, and 20 equals a times b to the 5th. I'm going to divide them out. I get 1,000 is equal to b to the 57th power. that means I need to take the 57th root of 1,000, and I get B is about 1.129. While I'm here, I'm going to answer this question. Well, this is definitely growing. So 1.129 minus the initial 1 is 0.129, which means I have 12.9% annual increase. But to write my equation, I'm going to do y equals a times 1.129 raised to the x. I could use any xy that I have. I'm just going to use a smaller one. 20 equals a times 1.129 to the fifth. And now I can just divide by 1.129 to the fifth. I could let the calculator do the hard work for me. I plug this into the calculator. I get a value about 10.9. So I have my number of snakes is 10.9, 1.129 raised to the x. And this is a model. This is not necessarily exactly what's going on. So my question is, how many snakes were introduced in 1940? Well, 10.9 is about 11. Obviously, there's no such thing as 10.9 snakes. And then finally, it wants to know, when will there be 75,000 snakes? So I could just take 75 is equal to 10.9, 1.129 raised to the x, 75,000 divided by 10.9. I get some weird fraction, 75. Okay, sorry about that. I had some kids stop by while I was making a video. So I did 75,000 divided by 10.9. I got 6880.7 about is equal to 1.129 raised to the x. So now I'm going to log both sides. This x goes in front. So x equals the log of 6880.7 over the log of 1.129. And when I do that, I get about 73 years. What the initial year was 1940, that would be the year 2013. So the next problem is going to model by a logistic function. So the idea is that we have a high school of 792 students. That means my max is equal to 792, which is important. A rumor is started by 9 friends, though that means initially I have 0, 9. That's important too. This is not the a value from this equation. And then I need another point, and my other point is at 10 a.m. I have 240 students. Well, 10 a.m. is 2 hours later, 240 students have heard this rumor started by these 9 friends. So since 792 is the max, I know y equals 792, 1 plus a times b to the x or to the t. I don't care what you do. Again, 0, 9 is not the a value. I have to figure out the a value by doing this. 9 equals 792, 1 plus a times b to the 0, and I chose this point because b to the 0 is just 1. These two can change spots, so 1 plus a equals, wow, I am mentally tired. 792, not 729, is going to be 792 over 9. I do that division, and that is what it gets. 88. Sorry about that. So I have 1 plus A equals 88, so A equals 87. So now my equation is, do it in purple, y equals 792 over 1 plus 87 to the bx. That's how far I've got so far. Now I got to figure out b by using this other point. 240 is equal to 792, 1 plus 87, b squared. That's putting an x and a y. Again, these two guys can switch spots. 1 plus 87b squared is equal to 792 over 240. I put that in my calculator, and 792 over 240 is 3.3. I subtract the 1, 87b squared is equal to 2.3. I divide by 87. I have b squared is equal to 87 over, again, sorry, 2.3 over 87. Square root both sides, and I get b is about 0.163. So now finally I have r equals 792 over 1 plus 87, 0.163 to the x. This is the formula on how this rumor is spreading around school. Okay, so I have this Lexus that costs $61,055, and it's lost 46% in 7 years. So that means there's only 54% left. So one way to write this is doing this, 0.54 t over 7, because this says it has lost 46% in 7 years. That is one way to do it. Another way to do this is take this 0.54 and raise it to the 1/7, and when you do that on the calculator, .54 raised to the 1/7, you get this decimal, which isn't always bad. 0.916, and I can rewrite this equation as L equals 6155, 0.916 raised to the x or raised to the t. They're about the same. The only difference is that this one is more exact, okay? Because it is incorporating a loss of 46% in 7 years, and that 0.916 is a rounded off number. Well, that does help me with this part, because I do 1 minus 0.916, and I get 0.084, which is 8.4%. That's what it's losing per year. But if I want to know the value after 4 years, I'm going to plug it in here. L equals 6155, 0.54 to the 4 over 7. And I get, which I don't know, I'm going to use my calculator. 61055, 0.54 raised to the 4 divided by 7. I get this number. And if I use the other one, 61055.916, which is a rounded off number, but now raised to the 4th, I'm going to get about the same. It seems like it's quite different, but that 0.916 is rounded. It actually was a little bit bigger than the other number, so there's a little bit less decay going on. So I get equals 42,983.63. That's the price. That's the value after 4 years. Okay, so I want to know how long it's going to be until the car is only worth $10,000. So I set up my equation, set equal to 10,000. I divided by the initial value. I got to log both sides. I'm just going to leave this as this ugly fraction. I want to work with exact results. I don't want to work with rounded off numbers. Well, this drops in front. So I get log of this ugly fraction is equal to t over 7 times the log of 0.54. So now I have to get rid of the 7 by multiplying by the 7, get rid of this by dividing it out, and now I'm going to put this into the calculator. So t equals 7 times the log of this ugly fraction over the log of 0.54. And I'm going to put this in the calculator and see what I get. 7 log of this ugly fraction divided by log of 0.54. 20.55, what was it, 20.55, whoops. A little bit less than about 20 and a half years, the car will depreciate down to $10,000. Okay, thank you for watching this video.